All right, so we've got the weekly announcements up here, and there's a lot going on. We're in the middle of finishing up that homework, and I know that's a challenging homework that, to be honest, people are just kind of leaving a little bit too late, in my humble opinion. I think if we started that one a little earlier last week, we wouldn't be in this situation, but that's okay. Here we are. This homework was extended from last week. It's now due tonight. I did a lot of those problems in class last week. I know people have been working on it over the weekend, have been talking to via email and Slack and all that kind of stuff. So I'm happy to look at a couple of those problems if there are still things you want to clarify there. You need to let me know right away, though. So let me know if there are things, specific questions you want to look at right now. As you get that together, I'll just remind you that we also pushed the quiz back from last Friday that I'd like to have today. If no other reason, I really need to assess whether or not the derivative part of these problems is causing people an issue. And so I would like to do that, even if it ends up being a take-home kind of thing. I've got it ready, and I think that would be really helpful just in terms of preparation for the test, for example, which is Friday, right? So we have our next test on Friday. There's lots of review material out there. I'm happy to look at some of those review material, but this homework that has been extended from Friday is the last topic on that test. And so we do want to make sure that we understand how to do the homework due tonight for Friday. There is also another assignment due Wednesday that was also pushed back from last week. I kind of separated it from the material that's due tonight just because that material is not technically on the test. And so if you need a little more time with that, that would be just fine. Okay, I'm seeing a couple questions in the chat. I'm happy to look at a few of those. Let me see which ones you're asking about in particular. So I'm seeing max, mins, number 9, concavity, number 13. All right. Oops. Love when I do that. Give me 1 second. Actually, let me take this out of my case. It's just easier to deal with it. It's not in there. So that problem number 9. Is it Kim who asked that question? No, it's Gregor. Let me take a couple screenshots and then I'll share my screen again. What I'd like to hear about are specific things that are confusing about those problems. I feel like at this point I've talked about the general how to do those things. And so let me just take the screenshots and then you can let me know what's up, Gregor. Concavity number 13. So concavity number 13, I think I started in class. We can talk about what's confusing about that one. Concavity number 4. Okay. All right. So I'm sending these into my PDF thing. Let me share my screen again. So let's talk about max, min, number 9. So what is it about this problem that's confusing? And maybe one of the confusing things is the fact that it gives you so many places to write your answer. And notice how it sort of says, if you don't need any, just put an n in some. So I'm assuming you'll put a bunch of n's in some of those spots. Is there something in particular that's tripping you up about this one? I think it was Gregor asked the question.
So in particular, I set 15e to the 3x equal to 0. And I remember us talking about setting e to the x equal to 0. You can't necessarily do that, right?
Right. E to the x looks, oh, that's e to the minus x. E to the x looks like this. Yep. And what we talked about was there's a horizontal asymptote at e to the x, which makes it never 0. Yep.
Yeah. So I'm just confused about like where do I go from here if it's not going to be 0?
So there's no critical points. It kind of looks like in this problem.
Yeah.
So I would say there's no critical points.
Mm-hmm.
Maybe people have different generated questions. It's possible someone else gets one generated that does have critical points, just to be clear, in case someone is seeing that. But in this particular problem, e to the x plus 5 is above the x-axis. It just goes up. There's no maxes or mins. There's no discontinuities. And so it feels like you just put an n in all the spots.
Okay, thank you.
And I realize that's a little funky, but maybe one of the things this problem is trying to get across is there's not always critical points on functions.
Okay.
Did anyone get a critical point in this one? Just curious if someone maybe had a different problem that did have a critical point. That might be the point of this problem is, hey, we don't always get critical points. Is that one okay? Other thoughts about that one? I see Sebastian is also asking about number 13 here. So before we move on to the other one, let's look at 13 real quick. So how did you approach this one, Sebastian? Are you having particular problems? Did you find critical points? Or where are you at in this one? It tells us we have 2 critical points. Are you able to find those? Sebastian, you with us? Oh, it's got trouble with the second derivative, I see. So the first derivative is just going to be cosine becomes minus sine. The x just goes away, and we get that, right? And so just to be clear, when we want that to be 0, what we end up seeing is we want sine to be root 2 over 2. And so this happens at pi over 4 points. And then when we take the second derivative, let me just read the question here. It's got 2 critical numbers. So these are the critical points right here that go in that spot. And then it's trying to get you to do the second derivative test on this part. And so it's saying, hey, when you use a second derivative with those points, what happens? That's how you figure out concavity. And so let's look at the second derivative, right? So the first derivative is minus sine plus root 2 over 2. And so when you do the second derivative, the constant's just going to go away and sine becomes cosine. And so when you find critical points, for example, so let me flesh out the critical points, right? If we want the y value of a function to be root 2 over 2, that happens at pi over 4 and 3 pi over 4. Because it doesn't matter what the x value is, but the y value is root 2 over 2 in both those spots. So I've been saying this quite a bit. If you need some help with trig, I can help you with that. One of my goals today is to prepare some review material. No one's asked me for it, despite how many times I've offered to help, but it's very clear people need help with that. So I'll take the initiative for you and get that done. So anyway, those are the 2 places we're looking for because it's got the root 2 over 2. So those are the critical points, pi over 4 and 3 pi over 4. So just to be clear, these are the critical points, not the pi parts, or these are the critical points. And so when we do the second derivative, we just plug those into there, right? Like f double prime of, for example, pi over 4 would be a minus cosine of pi over 4, for example, which is going to be minus root 2 over 2. And so that's telling us it's concave down. And so that means it must be a max. Oops. Sorry, I'm running out of room here. So I don't know if that's the kind of thing you're looking for, if the trig part's the tricky part, or feel free to clarify anyone. Okay, so I'm also hearing then, if there's a clarificational thing about this one, concavity number 4, and Kim is clarifying number 8 instead. I'm going to look at that. Is this one all right? Am I in the right place here? Yeah. All right, come on. Let's go back. Okay. Not that one, number 4. Let's start with 4. So this is just a question about inflection points. So I'm going to look for whoever asked that question to clarify in a second. Let me say quickly how you do this, right? F double prime equals 0. So solving that tells us inflection points. And then we would test some points in between them to figure out the concavity part, right? Because inflection points, the definition of what that is, it's where it changes concavity. It's where f of x changes the concavity. So what was the issue particularly with this one? I'm having trouble finding the inflection point. So the first derivative here is going to be 12 times 5. What is that? 60, 12, 24, 36, 48, 60. Of course, 60 x to the 4th. 45 times 4. What is that? 180? Please correct me if I'm wrong. Just doing this off the top of my head. And then 200 times 3 is 600. So that's the first derivative. Does that look okay? Seems okay, I think. And then the second derivative, 60 times 4 is 240. 18 times 3 is, what is that, 540? Can someone tell me? Double check that. And then we'd have 120x. Does that seem okay? Someone with a calculator able to verify those things for me? Pretty sure that's right, right? 1836, 54. Right?
Yes, it's correct.
Okay, great. So, you know, anytime you
Wouldn't
have
that be
a function.
1200?
I'm
Or
sorry, say it
sorry,
again.
or sorry.
Oh yeah, 1200. Yeah, thank you. Thank you. Yeah, 600 times 2, 1200. Yeah. Anything else that look okay? So anytime you want, and you want this to be 0, right? Anytime you're trying to solve this, it's anything equal to 0. If it's a linear function, i.e. power 1, super easy. If it's quadratic, i.e. power of 2, you either factor it or you use the quadratic formula. So also easy, or at least straightforward. If you have something in power 3 or more, it's hard. And almost always it's going to be you factor an x out or something like that to make the powers go down. And so notice in this problem, each thing you can factor an x out of this, and then it becomes a quadratic. And you could actually pull out a constant as well. I'm not going to think too hard about that right now, but you could pull a constant out as well, but this will work too. And that's how we move forward in this problem. All right, so we get x equals 0 from this one. And you use the quadratic formula on this one, or factor it if you want. But quadratic formula always works, and you'll get 2 more critical points. And so that's how that one works. So, okay.
So how come I thought we used the first order derivative to find the points?
So the points is not a good descriptor. What kind of points are we talking about? That's the key here, right? Is understanding which derivative tells you what. So what kind of points are we trying to find here?
Inflection values?
Inflection values. And like I wrote at the top of the page here, the second derivative tells us inflection values. What does the first derivative tell us? What's the other kind of points we find?
Critical points.
Max and mins.
Yeah, max, mins, or critical points is what we call those. F prime equals to 0 tells us critical points.
Oh, okay.
So yeah, that's an important thing that we really want to have straight in our head is, what is the difference between these two derivatives? What do those two derivatives tell us? Right, the first derivative tells us increasing decreases, which is how we find the flat points, i.e. critical points. The second derivative tells us the curvature, known as concavity. And so that's where inflection points come in. Other thoughts about that one? All right, I don't want to spend too much more time on these two homework sets here, but let me just bring up 8 here and see if there's something in particular. So this, you know, for example, this is the wrong homework set though. You were talking about concavity. Okay, is this one I started in class? I feel like it is. What was the issue with this one, Kim? Was it the derivative? What did I do with my things from last week? Oh, they're there. I deleted them accidentally. Let me move this here. I think I had started this one. Perhaps not. It looks very similar to the ones we did. It looks kind of like this one. Is this the same one? I think this is a little bit different. Okay. Anyway, where did that one go? Kim, could you tune in here and tell me what the issue with this one is, or I'm going to move on?
So for number 8 concavity, I think I'm just really getting stuck on the second derivative. I've like tried it so many times to get it correct, but I'm not sure what I'm doing wrong.
Okay, I don't know what the heck just happened to it, but let me do that again. All right, 4 hours later. So what'd you get for a first derivative?
So my my function was x squared e to the 5x, not 7x.
Yep.
For my first derivative, I got 2x times e to the 5x plus 5 times e to the 5x times.
Great. And so then when we do the second derivative, it's 2 product rules. And so the first one looks like f prime g plus f g prime. And the second one looks like f prime g plus f g prime. And you can simplify some things, but I'm just trying to write out the details.
For the second part, it was 5x squared times. Oh, okay. You rewrote it in a different way. Never mind. Sorry, got confused.
Sure, no, that's fine. So then you factor out an e to the 5x, and it becomes 2 plus 10x plus 10x plus 25x squared. And you don't get, and you want that to be 0, and you don't get anything from the first one. The e to the 5x doesn't be 0, right? You've seen that a bunch of times. You set this one to equal to 0, and this one you get 2 roots out of. Use the quadratic formula here. Maybe you could do it a different way, actually, now that I look at it. You might be able to factor this one, but quadratic formula works every time. You don't have to think about factoring. Does that clarify? Is that where you're getting?
Yeah. Well, I see where I went wrong.
Okay.
Makes sense. Okay, thank you.
Sure. And as far as finding the intervals of concave up and down, the first example in the notes today actually does that. And so, and we've done others, just to be clear. It's not like we haven't seen that before, but we'll review that in the first example in the notes. And I think I would like to jump over to that now, unless there's a question about this one. I'll just remind you, I've got office hours this afternoon as well, if someone wants to come and talk about it and finish your homework up then. Okay, and I will throw those into the homework solution folder. Try to remember to do that. So the thing I was talking about that might help with this is this rational function one. And I think there's at least one of these in the homework set, maybe two. And so let's find the critical points on this. We can look at concavity. We can do all the things that we've been doing with all these functions with this particular example. And maybe this will help clarify some of these questions that we're talking about. Let's do the concavity thing, for example. We can do all those things. So let's practice this one. So we're going to find the critical points first. And we know that critical points, as we just clarified a second ago, critical points are where the first derivative is 0. So we want to take the first derivative and set it equal to 0. And we also want to look for the first derivative or the function being discontinuous, right? Those are the two things for critical points. And again, we're just sort of talking about the homework problems, and it seems like people still need some clarification about the difference between the two things. Critical points are the first derivative being 0 or the function being discontinuous. And the reason I wanted to do this one is because it's a quotient rule, right? We've got a fraction. And so when we do the first derivative, we need to do the quotient rule. I mean, you could think about it as a chain rule maybe, but I'm going to do the quotient rule. And the derivative of the numerator is just 0. So that's kind of nice because it'll make it easier, right? And so the derivative ends up being f prime g minus f g prime, all divided by just whatever is in the denominator squared. Right? Hopefully we can think about the quotient rule and that makes some sense. And that's, like I said, it's not too bad because the 0 part just cancels out the square and we get not too bad of a numerator. I'm going to go ahead and multiply out the bottom because we're going to look at the second derivative and it would be helpful to have it multiplied out for that. And I tried to prepare you for this question a little bit on your own just by thinking about how do fractions become 0, right? We want this to be 0 somehow. And I tried to remind you last week that whenever we want a fraction to be 0, we just want the numerator to be 0, right? And so if we want that fraction to be 0, that just implies that 2x is 0 or minus 2x. And we just get x equals 0. And so it has nothing to do with the denominator, right? It just has to do with the numerator. We set the numerator equal to 0 to figure out fractions being 0. So there's only one critical point because the function doesn't have any discontinuities. Well, actually, let's think about that in a second. But let me see if that's the first part's okay. Okay, see that x equals 0 is going to be either a max or a min or maybe a point of inflection potentially.
What is the exponent and the denominator, the first x?
This is a 4.
Oh, okay. Thank you.
Anything else? Come on, there we go. So this is a fraction, so we should be careful about the denominator being 0, right? That is something we should think about. And so the function and the derivative don't exist, right? They have discontinuities when the bottom's 0. So whenever x squared plus 2 equals 0. And that's in both denominators, right? It's in the denominator of the original and the derivative. And so it's the same thing for both. Now, if we tried to solve that equation, we would subtract 2 and then take a square root, and we would get plus or minus square root of minus 2. Thoughts about what that's telling us here? Does the denominator become 0 ever? Is anyone sort of thinking about what that means? What do you think
Does
that's
it
telling
not
us?
exist because it's an imaginary number?
Yeah, right, exactly. So if we're trying to think about the location where that happens, it happens at some imaginary number. And so since this is an imaginary number, right, it's got a square root of a negative, the denominator is never 0. The other way to think about that is x squared is always positive, right? Because you're squaring it. Even when you plug negative things into x squared, they become positive. And so x squared is positive, and then you're doing +2. And so you're having a positive thing, you're adding a positive thing to it. You can't add 2 positive things and get 0. Right? So there's no discontinuities on this one because the denominator will never be 0. And so we would just say this implies there's no discontinuities. So pointing out that even in rational functions with denominators, there might not be discontinuities. So we don't get any discontinuities. And we just conclude that our only critical point is x equals 0. And so this kind of annoying looking function that's a fraction only has one critical point. Thoughts about that work at all? Does this seem okay? I hope people are wondering what this thing looks like. You know, I've mentioned this a bunch of times. It's always a good idea just to draw the picture, right? Graph it to know what it looks like. So I just graphed it literally just right now. And it turns out this function just kind of looks like a little bit of an x squared kind of thing. It does this. That's f of x. And so just looking at the picture, there's going to be a max at 0. And let's figure out, and it looks like there's a couple inflection points too, right? Actually, because it's concave down in the middle, but then it ends up being concave up on the outsides. So we're going to have a max in the middle. Let's see if we can prove that. And we'll have 2 inflection points. And so just kind of knowing what the graph looks like can guide our answer and make us feel either good about what we're doing or make us catch mistakes, right? So we'll classify it next. Are there questions about finding that critical point? We will, part B is going to be to classify. Anything in the chat? Nothing in the chat. Okay. So the thing that I'm going to ask you to do on Friday, one of the big things on the test, is finding the critical points like we just did, and then classifying them one of 2 ways, either using the first derivative test or the second derivative test. I'm going to do it both ways here. It's important. I'm going to ask you to do it both ways on the test too. So you need to know both of them, right? Now, hopefully the words themselves, first and second derivative test, tell you which derivative to use, right? The first tells us increasing, decreasing. And so we use that to think about like going up, flattening out, going down. And the second derivative tells us concavity. So we just like think about curvature. Is it curved down or curved up? Right? So let's do it both ways. So the first derivative test, you pick some values. Oops, wrong color here. Let me do that. You pick some values around your critical point and you plug them into the derivative, the first derivative. Right? And so our critical point was 0. And so you just want to pick something to the left of it, like -1, and to the right of it, like 1. Right? The idea here is like we know we have something going on at 0, so I'm just trying to go on either side of the critical point. Everything's okay so far? And as we just sort of clarified, I hope it was clarifying at the beginning of class, the first derivative tells us increasing, decreasing. Let's see if I can get this stuff to move a little bit, sorry. Darn it, I hate when that happens. All right, just forget it. So when we plug things into the first derivative, it tells us, is it going up or down, the function? And so when I plug -1 into the original function, it's going to be 1 over whatever x squared plus 2 is, right? So when you plug in -1, you get 1 over 3. Oh, I'm plugging into the original. Oops, into the derivative. The derivative. I just messed it up myself. Right, we're plugging it into the derivative. So we'll actually get 2 over 3 squared, which is 9. And so this is, well, let's write it the whole thing down. When you plug 0 in, you just get 0. And when you plug 1 in, you get minus 2 over 9. Again, I'm plugging it into here. And so this is telling us increasing or decreasing, right? This is telling us f of x is increasing, flat, decreasing at those locations. Increasing, flat, decreasing looks like this picture I'm about to draw. Increasing means it's going up, flat means it flattens out, decrease means it goes down. If we apply what we just learned here, we visually see we have a maximum at 0. Right? Based on all this information, x equals 0 is a max. Right? And we just classified it using the first derivative. And so on the test Friday, I'll certainly give you some functions and say, hey, find the critical points and classify them using the first derivative test. And this is the kind of thing I'm going to be looking for. Can I say anything about that?
So if there were more critical points, we just make another table. So a table for each critical point.
Exactly. Yeah, we need one table for each critical point. Yep. Other thoughts? Yeah, that's a good clarification thing. And just to kind of like, just to remind you where to look for that, right? We've definitely done that before, way back when we were doing this. Here was one that had 2, for example, right? This one had 2 critical points. And so we made 2 different tables there to kind of figure them out. So yeah, that's exactly right. Other thoughts about this one? First derivative test part?
What if you had 2 points and they were both concave down? So which one do you know it's max or?
So they're both concave down. First of all, that would be the second derivative test, but that would just mean they're both maxes.
Okay.
And we saw that actually in this example. Right, in this example, I know it's really messy because we did it all, but right, I'm circling on the right. There was 2 maxes. There was one here and one here. And we saw over here that they're both concave down. And so certainly functions can have any number of max and mins. And so keep that in mind, I guess. Yeah. That's good thoughts there. Other thoughts? Keep them coming. All right, let's look at the second derivative test. Let's make the exact same conclusion just using the second derivative. And so all we're doing is we're plugging things into the second derivative. So we need the second derivative, right? And so the second derivative is another chain rule. We're going to just differentiate the first derivative. And the first derivative is shown right there, still circled in blue, right? So it's just another quotient rule. And it's also not too bad. And so hopefully this makes sense. I'm going to just write it down. We do f prime g minus f g prime all over g squared. And yeah, this one's not as nice because you don't get the cancellation. But when you simplify that down, it's actually not too bad because the 2x just multiplies through there. And actually, you don't have to simplify it if you don't want. You could just plug things right into this. But I will simplify it just in case anyone's interested in that. So
Wouldn't the derivative of the second of the bottom be
say that one more time?
the derivative of x to the 4th plus 4x to the second? Wouldn't it be 4x cubed, not 3x to the 4th?
Thank you.
Second derivative.
Yeah. Yep. So this 4 should be a 3. Does everyone see that? I think that
And
was
then
the
the
issue.
3 should be a 4. You bring the 4 down, not the 3 down.
Absolutely. Yep.
Okay.
Thank you.
Sure.
So it's 4x cubed, right? So I was trying to take the derivative of this number, and you bring down the 4, subtract 1 off it, and it becomes 4x cubed. Thank you. Everyone see that right here? Clarify other things about that? Seems okay. That's right, yeah. And so, you know, again, you don't have to simplify this, but when I did, I got this. And one reason you might want to simplify it is just because it's a little bit easier to plug numbers into, which is what we're about to do. And notice how the denominator, thinking through these rationally, is helpful. The denominator has nothing to do with whether or not this is ever going to be positive or negative. The denominator is being squared. And so no matter what you plug into the denominator, it's going to be a positive number because you're squaring it. And so when you're plugging things in to figure out positive or negative, it really just depends on the top part, right? The numerator. And so just helping you think through how that works a little bit. And we're plugging in 0 anyway, so plugging in 0 is not that hard anyway, right? So let's plug in the critical point 0. All the x's go away. You just have like 2 times -4 over 4, and so you get -8 over 16. And all we really care about is that that's negative. And that's important because that's telling us it's concave down. And if we're at a flat place that's concave down, it must be a max. And so that's how we could figure that out using the second derivative. What can I clarify about that? Anything there? So when solving for this on, someone asked in the chat, solving for this on a quiz or test, do we need to use one of these methods to find concavity, or you specify which to use? So we haven't found, I'm going to do the concavity part at the end. Usually I specify, say, you know, find the critical points and classify them using the blank test, the first derivative or second derivative test. Can you explain how you simplified? So to simplify, you just combine like terms, right? You distribute the 2 through there. These 2 things cancel out, right? The 2 negatives would cancel because you're multiplying. And then you would distribute the 2x through there. And then you just combine like terms. And that's a bunch of algebra that maybe you haven't been in practice doing, but I'm sure you've seen all that kind of stuff before. So the only thing I wanted to finish with on this problem, well, we'll do the concavity in a second, is just to clarify that we found there's a max at 0. But what is the max? So we figured out the max takes place at x equals 0. But what is the max value? Well, if you want to find the max value, you need to plug that into the function. So the max value would be what you get when you plug that into f. And so that would be 1 over 0 squared plus 2, which is 1/2. So this is the biggest the function gets, is 1/2. And so that peak up on the picture, I won't scroll up there, but if you look at the picture, at that top of the peak, the highest point is just up at 1/2. I will label it real quick, right? If we look here, we're just saying this point's 1/2 right there, right? All right, I will look at concavity as well here. Can I clarify anything else first? I have to restart this real quick. I'm sorry. So points of inflection happen wherever the second derivative is 0. That's the last thing I was going to look at. So part C, for points of inflection, you just solve the second derivative equal to 0. And we have the second derivative right above there. And we know we just need the numerator to be 0, right? And so the second derivative equals 0 when that numerator equals 0. Has nothing to do with the denominator. We just take the numerator and set it equal to 0. And it's a, it's a fourth power 1. And so you just take this part and you set it equal to 0. And that's that you can actually factor that one. Right, this factors into 3x squared minus 2, x squared plus 2. Right, and we always like to factor because then you just set the factors equal to 0, right? You're just kind of moving down the chain here and figuring out what do I need to be 0, and you're just moving forward in this process by factoring in this case. And so we get a couple answers out of this one, right? Either this one's 0. Oops. Or this one is 0. Well, we just said a second ago, you don't get any answers from this one. Because x squared plus 2 is never 0. You're adding two positive things together. And so we get two answers from the other one. Add 2, divide by 3, right, to take the square root, and you'd get plus or minus square root of 2/3. And so these are the inflection points.
Professor, I just have a question.
Yep.
So why did you take out the 2 in the beginning? You know what I'm talking about?
I think it just, when I simplified it down, I noticed there was a common factor and to get to this point. You could just leave it. You could multiply that back through and get the same answer, if that's what you're asking.
Really? Oh, okay.
Yep. Yeah, so if you multiplied the 2 through there, you'd get, this would just be 6 and 4 there instead.
Okay.
But you end up with the same thing.
Okay.
Also, just sort of clarify, on a test, I'm not going to rake you over the coals with algebra. But, I feel like a lot of times people are like, oh my God, he's just flying through this. How is he solving this? And without being rude, this is the kind of stuff that you learned in a past class. And there's no simpler way of saying that. I'm happy to go over it. We can talk about how to do that in office hours. I can give you reference material, but we can't just continually talk about algebra forever because we're in calculus now, right? And so we need to sort of understand algebra to move on to future classes. And that's what we're doing here. I don't want to discourage anyone asking questions. Those are the kind of questions you need to ask. And, when your education is your responsibility, if you need help with that, then please get some help. But that's algebra from past classes that I'm not going to go over all the details for all the time. So anyway, I just thought I'd mention that. Can I clarify something though? I'm going to just finish this one off here. So those inflection points, what we just figured out are, we just labeled this place and this place, right? That's minus root 2. Even though my picture's a little janky, but it's okay. And so we can verify that by testing it in the second derivative if we wanted to. So we could create a table at those 2 points and figure out exactly what we just saw in the picture, right? So we just found these two being the inflection points. And so we could test a point to the left and to the right. Like, for example, -1, 0, and 1, right? We could test these in the second derivative to tell us concavity. Just like the first derivative test, but with the second derivative, right? When you plug a -1 into the second derivative, you would get a positive number. And so that's telling us concave up. right? When you plug in 0, you get a negative number, which is telling us concave down. And if you plugged 1 in, you get another positive number. I'm sorry, the first one should be, oh, that's right. Yeah, that's good. And so usually there's two things that trip people up on this stuff. Yes, taking derivatives and stuff like that is its own beast, and hopefully we're getting the hang of that. But things that trip you up from past classes are things like knowing algebra and being able to factor and solving equations, and then just knowing the basics of what the derivatives are telling us. Like, oh, the first derivative tells us increasing, decreasing. If you don't have that sort of firmly in your mind, then the first derivative test doesn't make sense, right? And you're just memorizing something. Same thing with the second derivative test, right? If you know that the second derivative tells us concavity, then right off the bat, that should be like, oh, okay, well, that's right. Well, if I test a critical point and it's concave down, it's got to be a max. So just understanding the basics of what the derivative is telling us, I think, is vitally important in this instance here. All right, what can I clarify about that? I'll have to say something else if you've got something. Don't see anything in the chat. I'll just wait a minute here.
I have a question.
Yep.
In a test, if we understand the theory that we know that those are inflection points and we know that at 0, it is a max.
Yeah.
Do we have to do like plugging in points in between if I understand that it is concave down at 0? So at the other end of the inflection point, it would be the opposite, concave up? Or
Yeah, that's a good way to put it too. Yeah. So I'm not sure. I think Diana was asking that, which is if we know the middle point, and I was talking to someone about this in office hours. If we know the middle point is concave down from this part, the second derivative test, right? The second derivative test told us it was concave down. And so that told us this part looked like this, like this. And then if these are inflection points, that means it has to switch concavity. And so if we know the middle part's down, that means the ends have to go back up based on the definition of an inflection point. So that's a really good point. Yeah. What I'm just trying to do here is look at these things independently, right? Like one question might just say, figure out where the inflection points are and determine the concavity. And so in other words, you might be asked to kind of do this page without having this kind of information. That's sort of the way I was thinking about it. But you're absolutely right. Yes, if you already did the previous page, you don't need these end pieces because you already got the middle piece, and that implies the end, is what you're saying, which is true. Good point. Other thoughts? All right. I would like to, I think we've got plenty of time for this other page here. And, you know, this is, and I really want to do this right now, especially not push it off anymore, partially because the schedule dictates it. But if this makes sense, if this page makes sense, and oftentimes visual things help, which is what this page is, I think it'll help, you know, solidify some of the concepts. I'm hoping it'll solidify some of the concepts for you for the test. Again, this is not on the test, so everything forward here is not on the test on Friday, but the material is applicable because it has to do with like the first derivative test, for example. And so, you know, this page is all about sketching specifically the function, so the original function, using information about the derivative. And the idea is exactly what it says right there, which is just reiterating the same thing I've said at least 3 times already today, right? Which is that the function, or the derivative, excuse me, tells us increasing or decreasing. And it tells us where the max and mins are because we find the critical points, right? And so this part here is just talking about the derivative being 0, right? And so we can use that information to sketch a general shape of the function. We're not getting like beautiful pictures here, just to be clear. We're just going to sketch the shape. And so let's just do an example here. Let's suppose this first derivative test gives us this sign chart. So you do a first derivative test and you end up with this. So here are our points we're testing out. I'm just kind of making this one up. I mean, I made it up ahead of time, I'm not making it up on the spot, but let's say we're testing these points in a table, -6, 5, 4, 1, 2, 3, 4. And forget about what the specific outputs are, but let's say that when you plug in -6 into the derivative, you get a positive number. At -5, it's 0. At -4, it's negative. At 1, it's negative. At 2, it's 0. At 4, it's now I'm confused. -4, 1. Oops, I messed it up. Sorry. So I just erased a few things. At 1, it should be 0. Yes. At 2, it's negative. At 3, it's 0. At 4, it's positive. Okay, I'm just going to let everyone finish writing that down because this is the kind of thing that you might want to look at. And the other thing we should just note here are the 0 places, the 3 zeros. Those are the critical points. Because the first derivative is 0 there, right? That's by definition, that means it's a critical point. And so usually this is the kind of thing that we end up with, right? We just did it a second ago, right? We just did it literally right here. It's like an extended version of this thing. Like I think Jorge was just saying, it's like here we have 3 critical points instead of just 1. Now you notice every time I make a table, I also make the table like horizontal, right? In other words, I usually rewrite it side to side. And so I'm going to do that same thing where we talk about the derivative and the x values. All right, let's make a number line is the way people oftentimes think about this. Do people agree and understand that the x values -5, 1, and 3 are the critical points? Is that okay? Because the derivative 0, the first derivative, that's right. And so those are the 3 things I'm going to add to this table. -5, 1, and 3. Because those are our critical points. And what we just did is we learned increasing, decreasing between each one of those points. Right? To the left of it, the first derivative was positive, which meant it was increasing. Between -5 and 1, it was negative, which meant it was decreasing. Right? Between 1 and 3, the derivative was negative, which also means it's decreasing. And then past 4, it was a positive, which means it's increasing. Right? So I'm just kind of rephrasing that table as a horizontal thing so that we can think about increasing, decreasing, right? And draw a picture. That's what we're eventually moving towards right here. So I'm going to put it all together in a picture in a second here, but are there questions about what I'm trying to write and sort of say here? Let's see. This is like after we did the first derivative test, this is the kind of thing we would have. And we can use this to draw a picture is what we're getting at. Questions about what I'm trying to say at all so far? So if we put it all together, everything in the table there, it would look like this. And I would encourage you just to maybe focus in on what I'm writing just for a second here. How's a good thickness? That looks good. So increasing until 5, at which point it flattens out and then decreases, right? So it would increase until 5, flatten out, and then start decreasing. And then it's going to decrease to 1, flatten out, but then decrease again. And then flatten out at 3, and then increase. Right? And so we're lining up sort of these critical points with the flat spots. And then the increase, decrease is the in-between places. And if we graph this function, it would generally have that shape. And we don't even have the function in front of us, right? So we're just doing this really abstractly, excuse me. But it would have kind of a peak over at -5. It would have an inflection point in the middle. right? Let's label a few of those things. We would have a max right here. This is showing you an inflection point, right? This is showing you a min. And so this would be a sketch of the function. What do you think about that? I feel like that makes sense. You're in okay shape for the, you understand the first derivative test at least, right? Like this is the kind of thing that the first derivative test tells us. Increasing, flat, decreasing, that means we've got a max. And all we're doing now is saying, okay, well, let's draw it, right? Decreasing, flat, decreasing, that would be this piece, right? Decreasing, flattens out, decreases. And I didn't do the best job there, but you get the idea, right? It was going down, flattened out, and then started going down again. And notice how it was concave up before and concave down after, right? So it's a point of inflection. Does that seem okay? All right. Try this one. So let me draw another, let's see here. So I'm going to make another table. Let's see if I can just separate this a little bit. And let's make this table. So let's say our critical points are the ones I'm writing right here. So -1, 0, 2, and 3, those are our critical points. And let's say when you plug them into the derivative, right, these are x values down here. These are going to be first derivative values. Let's say you get the following. You get plus 0, plus 0, minus 0, plus 0. And there's a plus on the outside there. Right, what would that look like, right? So the pluses, the first derivative tells us increasing, decreasing. So pluses mean increase, minuses mean decrease, and then 0 means it flattened out. Right, so using this information, we should be able to get a general sketch of this thing. I encourage you just to see if you can sketch something on your own piece of paper and see if it looks kind of like what I'm about to draw. Or if you're a little confused, this is a good time to ask a question. Excuse me. I'm not seeing any questions here. So when I'm drawing this one, I see increasing, flat, increase. So increase, flatten out, but increase again, but then flatten out by 0. Right, and then we're going to decrease, flat, increase, flat, increase. Did I do that right? Decrease, flat, increase, flat, increase. Yeah, that seems okay. So there's an inflection point, a max, a min, and another inflection point. What do you think? All right, there's one more version of these problems that you should be aware of, which is ones that have discontinuities. And so you can see in this last example, it says, assume the discontinuities are infinite discontinuities. And so you could potentially end up with a table that looks like this. So let's say our critical points are -2, 0, and 1. But then when we go ahead and we do the first derivative test, we end up with -, 0, positive, but then you get a discontinuity at 0. This is the new part of this one, right? The DNE in the middle. And I'll remind you, critical points either happen at flat locations, i.e. derivative is 0, first derivative, or discontinuities. And so this is one that has a discontinuity, and we're being told that the discontinuity is an infinite discontinuity. And so infinite discontinuities happen at vertical asymptotes. And so we're just being told on this particular problem that when we go ahead and we graph this thing around 0, there's a vertical dotted line at 0, and the functions are either going to shoot up to infinity or down to negative infinity or something. And the sign chart tells you which one it does, right? And so we just do the same thing though, right? So negative, this first part, negative 0 positive means decreasing, flatten out, and then increase again. And then we're having an infinite discontinuity. And so it's just going to shoot up to infinity. And then since we're moving left to right, this next part being negative means that it's going down, and it's coming down from the infinite discontinuity. And so that would be like this, right? Going down, flattening out, and going down again. And so in this particular one, you see we have a min here, and then this ends up being an inflection point. This is our sketch of the function. What do you think? Does it seem okay? I wanted to look at one of these from the homework as well. And so that's what I was going to finish with, was looking at the homework problem. Anything I can clarify there at all? Okay. So one of the homework problems, and these manifest some ways in themselves in different ways in the homework, but I thought it would be worth looking at least at this one, because this one is kind of confusing, and I think this is one of those problems where it's not super clear about telling you like what problem's right and wrong. And there's a lot of answers in this one, right? So each one of the, this is a problem number 5 in the information about function from derivatives. And each one of those question marks down at the bottom, each one of those series of question marks is a drop-down menu. And each one of those drop-down menus has different options. And so I'm trying to tell you which options each has using the color-coded annotation. So for example, I'm using blue, right? This thing right here in blue at the top is showing increasing, decreasing, or constant. So the things that are highlighted in blue down below have those 3 options, either increasing, decreasing, or constant, right? Things that are highlighted in purple have the options nothing, local max, local min, or inflection point or corner, right? Things highlighted in green have the options concave up, concave down, straight. And then the red options have the options plus, minus, 0, undefined. And so I'm just trying to, show you what the options are color coded wise. Is that clear? I know this is a very confusing looking image. And so does that make sense? Or can I clarify something about that? And I think everyone has a different picture here too. So it's important that you understand what I'm doing in this picture so that you get your own correct. And I'd like to get those options back. So I'm going to quit this and get that back. I want to insert another page so I can make a couple notes. So the couple notes I want to make just really quick is that f of x is the function, obviously. It's the normal function. F prime tells us how f is increasing or decreasing, right? The thing that is particularly confusing about this one has to do with the second derivative. So the second derivative tells us a lot. It either tells us concavity of the original, or how the first derivative is increasing or decreasing, right? Because when you take the second derivative is the derivative of the first derivative. I know this is, if this notation is hard, let me know. But since derivatives tell us increasing, decreasing, like I just said, the second derivative is telling us how the first derivative is increasing or decreasing. And so that's something that we haven't like worked on in particular. That's kind of new in this problem. I was trying to get you to think about that. I've certainly written that down before, but I know that's not super clear. And so let's go through this real quick and think about which one of these things is happening. All right, so I'm not going to be able to, I'll have to flip back to that, right? So let me maybe just highlight the points that we're talking about. We're talking about -3 is one of the switching points. So each one of these points is worth 2. That's another thing to remember, right? There's -3. What else are we talking about? -3, we're talking about 0. We're talking about 4. Right, so talking about these kind of points here. I guess that's it. Okay. Questions about the setup? It's a confusing problem. I'd love for people to kind of focus in and let me know if there are questions. What would be the best way to write on this? If I make this kind of thick and I write on top of there like that, that should be fine, right? Yeah. So let's look at the function itself, right? So the first thing in the blue spots, let's look at the first line at the blue spots. So the blue options are increasing, decreasing, constant. At -3, the function is decreasing, and it decreases until 0. And so this is going to be decreasing, decreasing, and then from 0 to 4, it starts to increase again. And then bigger than 4, it's still increasing. Is that okay? And so then the purple parts are talking about, is it a max or is it a min? Is it an inflection point? And it wants to know at -3, 0, and 4. So 0 is clearly a min, right? We can kind of see that. So I'm going to put min at 0. But then the other two places are the inflection points, right? It's concave up in the middle, but it's concave down on the outside. Should we label that real quick? Right, like down here, from here to here, this is concave down. This part is concave up in the middle. And then from here to here, it's concave down again. Right? And so this is going to be inflection point. Does that first row look okay? Right, so -3 and 4 are the inflection points. That's where it's changing concavity. And so hopefully we can answer the second line then too, right? The second line is just about the function.
So this is what we were supposed to do for the homework.
Hey, Jeanette, welcome to class. This is homework problem number 5. Going over problem number 5. Can I clarify something? Is something else confusing? I don't know what you mean by this is what we're supposed to do for the homework.
Yeah, never mind.
Okay. Anything else? So we just talked about, concave up or down, so we can fill in the second line, right? So less than -3, it's concave down. Between the 2 points, -3 to 0, it's concave up. It's concave up, and then it goes concave down again. All right. Let's do the other blue part. Actually, no, let's do the red parts, I guess. Let's do the red parts. So the red parts are plus, minus, 0, or undefined. Those are your options in the red question marks. And so if we're looking at the derivative, the question is the derivative positive or negative? Right? And so the first derivative we just said tells us increasing, decreasing. So increasing means the first derivative is greater than 0, which would be plus. Decreasing would mean the first derivative is less than 0, right, which would be a minus. And so we already know about increasing, decreasing, so that tells us the answer to the next one. Right? In other words, this decreasing tells us that the first derivative is negative. This decreasing tells us the first derivative is negative. This increasing tells us the first derivative is positive. This increasing tells us the first derivative is positive. Right? What about those middle parts? What about so it's 0, or I'm sorry, -3 and 4 were the inflection points, and 0 was the min. Thoughts about those? I'd love to hear from someone. So first derivative, right?
Those would be considered flat points, so they'd equal 0.
So the bottom one is 0, right? It's a
Okay.
oops. At 0, we've got a min.
Mhm.
So that means the first derivative is 0, but it's not 0 at the other two, right? It's the kind of inflection point where it's still going up or down.
Okay.
So at -3, the function's still going down. Yes, it's an inflection point, but do you see at -3, it's still going down, right? So this is still negative here. And this one is the opposite. Yes, it's an inflection point, but it's still going up. In other words, the other way to sort of think about that is you've got 3 pluses and 3 minuses in a row, right? You couldn't have something other than a minus or a plus between them without having a critical point, another critical point. Thoughts about that first line? Or that middle line, I guess? I guess this is really, oops, that's not what I meant to do. This one's telling you this, right? This one's telling you this one. What about the second to last line? So there's only, there's some spaces in there and they're blue. So blue is increasing, decreasing, or constant. And so let's look at this idea. People are welcome. I know I might go over a minute over or something. I know we're at the end of class, so if people want to leave, that's fine. But I'm going to finish this one incomplete. If the second derivative tells us how the first derivative is changing, right? So f prime increasing, that would imply that the second derivative is positive, right? And the second derivative decreasing would imply the second derivative is negative. In other words, concave up and down. So this is definitely a challenge part of this question. It's getting us to extend this idea. Do we understand the relationship between the function, the derivative, and the second derivative, right? F prime increasing means the next derivative is positive. And so if the next derivative is positive, that means concave up. And we already know things about concavity, right? Do people see what I'm saying about that? I'm going to, just kind of page back up here and look at it then. So we already have concave up or down sort of fleshed out. Let me switch my color. And so this concave down part is telling us that the derivative must be decreasing, right? This concave up part means that the derivative must be increasing. Same thing here. Do people see what I'm saying there? if that's okay, let me go ahead and finish the last part. The last part then is just the second derivative, and it's plus minus 0 undefined, right? So the second derivative being plus, we've just said it a couple times, means concave up or down, right? So this kind of thing. Second derivative tells us concavity. And so that's what this is telling us. At each location is a concave up or down. And so we use the same information to do those ones, right? So this is going to be plus. This one also means a plus. I'm sorry, the first one should be a negative. It was concave down, my fault. Oops. I'm going to do all those. Concave down means the second derivative is a negative. I apologize. Right. And then the in-between places follow that same situation, except the in-between places are inflection points, right? And we know that an inflection point is where the second derivative is 0. So the last thing I'll do is this one is telling us this is 0. This one's telling us this is 0. This one's telling us we've got a min, it's a plus. So I know that's super messy here, but the idea is all these things are interrelated, right? They're all telling things about each other. And so this is, I know, a complicated, annoying, kind of tedious problem, but if each one of these things makes sense, this is the kind of problem where it can really help clarify your understanding, in my opinion. And I'll emphasize again, everyone I think gets a different picture. And so try to translate what we're talking about on this one to your picture. And I'm happy to look at yours if you want. Some of the pictures are kind of tricky. Like some of them have straight parts, right? There's no straight parts in this picture. They're all curved. If you've got a straight part, that's kind of tricky. I think, for example, Gregor had one like that. All right, so I'm way over. I'm happy to stick around if you got some questions, but I'm done. Let me know if you want to. I'm happy to talk about this one. Questions about this one?
Could we take a look at mine?
Yep. Can anyone have questions about this one in particular? I'm glad you think so, Rory. Do you want to share your screen or you want me to pull yours up? I don't know what would be better.
I think it'd be better if you pulled it up.
Sure. I'm going to record it and post it if that's okay, Gregor. I think it might be helpful for other people.
Totally.
Because if I remember correctly, yours has that straight part. Is that right? Or maybe not. I must be thinking about someone else. Okay.
It does have a flat point at the inflection right at the bottom. Is that an inflection point? If I have that correct. At, what is that? X equals -7.
Yes.
Yeah.
Yeah, no, I just meant there were some graphs that they have a straight part and then they get curvy, and I don't really yeah, I see what you're saying with the inflection. I just mean it's not it's not as confusing as it could be, believe it or not.
Okay.
All right, so do you want to just run through it? Do you have a specific question?
So I don't have any specific question. I'd prefer to just run through it because there was a lot in that other one.
Yep. Let me just sort of label the points again. That was helpful for me.
Okay.
So this is one of the points. 0 is one of the points. 6 is one of the points. Okay. It's just kind of helpful to break it up because now I'm seeing it goes concave down to concave up to concave down.
Being able to mark it up is really helpful.
Yeah, that last part, it might be straight actually. That last part is real funky looking. Let me just pull your answers up too in case we need them. Right, that last part looks like it goes down and then back up again, which means it
Yeah.
would be another critical point. So that's probably not true. So that's definitely a little funky. That's one of the, let me just look at the answer to the last part. I guess the question is, past 6 is the second. Yeah, so I think this is, it's saying that this is a straight line.
Oh. It looks sort of curvy. I don't know.
It looks bumpy as heck. Yeah, I mean, it looks like
Yeah.
it goes up and down. But
Okay.
what I'm seeing from the answers is that constant, then 1, 2, 3, 4.
So,
That's a straight line. So that'll help us clarify that.
okay.
So then, yeah, go ahead. I agree
Oh,
that, do you want to just go
so-
through one by one?
Yeah, sure. So starting at x is less than -7, it looks like it's increasing. Then it hits that inflection point. It flattens out.
Yep.
Then it's increasing again.
Mm-hmm.
Then it hits another inflection point.
Yep.
And the inflection points don't have to necessarily be flat, right?
Correct, right? There's this kind of inflection point, which is sort of flat.
Mm-hmm.
And there's this kind of one, which is not flat.
Okay. And that's going up and then down.
Right. So the way we were
Is what
clarifying
it's
that
trying to
before
say.
is on the one on the left, the first derivative is 0 and the second is 0. On the
Okay.
right, the first is negative and the second derivative is 0. All
Okay.
right. So 0 to 6, I agree, is also increasing.
Then
X
at
equals
6, what are my options for that actually? Would that be another inflection? I'm not sure with the straight line being after it.
I know it's a little funky. I believe that is actually an inflection point. Let me just look at the answer. Yeah, it's trying to get an inflection point because it changes from concave down to no concavity, which I suppose is
Okay.
technically a change there.
And then after
And
that,
then
what would I?
increasing. It's still increasing, right? It's just going up. So the difference,
But
the
it-
thing that I'd like to maybe jump at right now, and maybe what one of the confusions is, it's increasing past 6, right? It's still going up, but it's increasing at a constant rate now, right? Straight lines have a constant rate of change. And so
Yeah.
on that interval, I didn't take a screenshot of the whole picture like an idiot. So, but on that interval, it just means that this is telling us that the first derivative is going to be constant at that one. I'm not gonna be able to write there either because I didn't take a good picture. Shit. I'm gonna just take another picture, unfortunately.
Okay.
Okay. So what I was trying to say was increasing, that's correct. That implies
It's
so
going
increasing but a straight
up.
line. So that just means that this one is constant, is what I was trying to say.
Okay. And how would we write constant?
I think it wasn't that one of the options.
For that one, no, it's plus, minus, or 0.
Oh, the derivative is plus. Right, it's
Yeah.
increasing. Sorry, that's
Okay.
right. The thing I was trying to point out was that the second derivative will be 0. So anyway, maybe I'm jumping the gun a little bit. We can keep going. So this is good. All right, 7, concave down looks good. Concave up,
Mhm.
concave down. This is the problem though. So this is no concavity.
So that's just straight.
Yeah, straight.
Huh. Okay. So now f prime. The increasing tells us what that'll be, right?
Correct.
Okay, so if it's increasing, it's plus, it's going up. If it's at the inflection point, from what I can see, it's a 0. It's increasing at that point. Inflection, it's also increasing there. It's not flat.
Yep.
Increasing again. increasing and then again increasing constantly.
Correct. That looks good.
Okay, and then the concave tells you what's underneath that. So concave down would be decreasing.
Yep.
Concave up would be increasing, down, decreasing, and then straight, constant. There you go.
Yep.
And then for
yeah, go ahead.
very end, what did the concave down also tell you what that would be?
Yep.
Okay, so that would also be negative 0 plus plus negative plus and then that point. Is there another option? That would be plus again.
Yeah, so it's minus 0 plus this. What did you say about this? Is a 0 one, right? This is an inflection point.
That's 0. That's not increasing.
Right.
Why is
Second
that the
derivative.
case?
Yeah.
Sorry, why is that the case?
Minus 0 plus 0. Because it's an inflection point. So f double prime equals 0 at inflection points by definition.
That's right.
And so yeah, minus. And then these two are also both 0 as well because it's straight.
Mhm.
And then I think that's good.
Cool. So it looks like the only parts that I struggled with were, I guess with that understanding that n bit, f, the second prime. What does that tell us again?
The second derivative tells us concavity. So if it's straight, there's 0 concavity.
Mm-hmm.
Right,
Okay,
the other
and
way to think about that is if you have a straight line, it has the function mx plus b. When you take a derivative, you get m. When you take two derivatives, you get 0. Because it's a constant.
Okay, and those are also critical points?
The second derivative?
Mm-hmm.
Critical points only come from the first derivative being
The
0
first. Okay.
or discontinuities. But generally, we think about them more as being the first derivative being 0.
Okay. I get that. Thank you.
Sure. Was everyone
for
else
your
doing
time.
other questions about this one? Janetta, Jack, Rashid?
Have a
No,
nice day.
I don't have any.
I just want to ask what was gonna be on the test on Friday.
So there's a very long, not long, there's a detailed document of test topics in course documents on Blackboard and also in the Drive, the Google Drive.
Okay.
There's a folder on Blackboard called Test Topics, Practice Problems, and Solutions.
Okay. Well, thank you.
Anything else, guys? Oh, I've got to get run into a meeting here. Can I clarify anything else? Yeah, go ahead.
Test be at like 3 separate times as it was last time, as in like 12:30, and then there was one at like 1:30.
So I set that up last time because there was snow. I would appreciate if it would come to either 11 or 12:30 or your normal class.
All
time.
right, I was just asking.
Yeah, I'll try to clarify that too. I actually forgot about the quiz today too. I'll just send the quiz out as a just practice thing.
Would we turn it into Gradescope?
The quiz?
Yes.
It's just going to be a practice thing. It'll just be for your review. Maybe I'll even send out the solutions with it.
Okay. All right. Thank you.
All right. Take care, guys. I've got to get running.
You too.